Y yo tengo que compartir pantalla, ¿no?
Ya está grabando.
Okay. Thank you very much. Good morning. I think we can start. Today, this is a new colloquium in the Instituto de Astrofísica de Andalucía. And today we have the talk by Dr. Núria Miret Roig. She will talk about a rich population of free-floating planets in Upper Scorpius. Núria will be introduced by our PI, Isabel Marquez. Isabel, please.
Thank you. Hello, good morning, everybody. Thank you very much for being here again in this new Severo Ochoa web colloquium, hybrid format now. It's a pleasure for us to have with us Núria Miret Roig. She did her undergraduate studies at the University of Barcelona, where she had her first experience as a researcher with the Gaia team. Then she moved to Bordeaux in France to pursue her PhD that was entitled Cosmic Dance, which is nice, a comprehensive census of nearby star-forming regions under the supervision of Professor Hervé Bouy. This work, focused on the low mass end of the initial mass function, is particularly free-floating planets, has been awarded with the 2022 Merak Prize from the best PhD thesis in the category of observational astronomy, and has also deserved the Science and Technology Thesis Prize from the University of Bordeaux. Núria Miret is author of about 35 papers in peer-reviewed publications, and currently she's a postdoc at the University of Vienna. She was a tutor at our Severo Ochoa Advanced School on Star Formation last autumn. Núria, thank you very much for accepting our invitation that I take the honor to extend to the next meeting that we will have in October, if you will be able to come here again. It's a pleasure to have you with us in person, and it's an opportunity as well for our young researchers, especially to be with you and to talk with you, to interact with you in person, as we were expecting, all of us. Thank you very much, and the floor is yours.
Hello, good morning. Thank you very much for inviting me to be here in Canada. It is a great pleasure for me to have the opportunity to be here in person, and I hope that afterwards we can have a discussion on all the work that I will present today. So indeed, my idea today is to present the most important result of my PhD, which we recently managed to publish in the review Nature Astronomy, which is related to the discovery of a rich population of free-floating planets in the region of Upper Scorpius, and which has been possible thanks to the collaboration in which my PhD took place. And I would like to acknowledge now all my collaborators. Okay, so I would like to start this presentation by mentioning the key ideas I will discuss today and I will present today. So first of all, I will present the discovery of a rich population of free-floating planets. I will explain you the research that we did that led to this discovery. Then I will explain how the mass function can help us to understand better the star formation theories and can help us observationally to constrain these theories. And finally, I will talk about the importance of precise stellar ages. Okay, first of all, so my goal is to understand how do stars form. And here I show you an image of the region of Ophiuchus, where star formation is presently ongoing. Stars form in the densest clouds when basically a clump of gas becomes gravitationally unstable and begins to collapse under its own gravity. In this scenario, stars also form at the same time as planets, and planets are the lightest products of star formation. They are thus highly sensitive to dynamical interactions, and for this reason, they give us also precious information regarding the initial conditions in which star formation takes place. For instance, they can give us a lot of information on stellar feedback. And so while star formation process is currently more or less well understood, there are still a few physical processes to be settled, like the exact role of magnetic fields, feedback, or turbulence, but I would say that the overall picture is well understood. When we move to substellar objects, this is still a highly debated topic. And the reason is that several mechanisms have been proposed to explain the formation of such substellar objects. For instance, it has been proposed that brown dwarf and free-floating planets could form similar to low-mass stars by the contraction and collapse of small clumps of gas. It has also been proposed that brown dwarfs and free-floating planets could form in the circumstellar disk around a star. And finally, due to dynamical instabilities, be ejected from the parent system. Also, we can think of a scenario in which several cores are accreting material from the same gas reservoir, and then dynamical interactions between these cores can end up with the ejection of one of the cores, which eventually will not have enough mass to become a star. And finally, also at the vicinity of very hot massive stars, the strong winds of these OB stars can evaporate the envelope around a small core, and eventually the small core will not be able to accrete enough mass to become a star. So while all these mechanisms have been proposed, and in fact they have been proved to be able to form substellar objects, now the key question is, which is the mechanism that dominates, and whether this is a universal answer, or different regions, in fact, in different regions with different conditions, different mechanisms can take different important roles. And to try to answer these questions, now I will try to convince you that the mass function is an important parameter that can help us to tackle this question. So here you are seeing different objects from the most massive OB stars towards lower mass objects, the sun for reference. And when we go to lower mass objects, we find the brown dwarf regime, and finally the planetary regime, to which I will be referring as free-floating planets. Those are planetary mass objects which are not bound to a more massive star, but on the other hand, they are just roaming freely on the galaxy. And so we have these different types of objects, and eventually the initial mass function tells us which is the exact proportion among different types of objects. For instance, it is well known that very high mass stars are very rare. On the contrary, low mass stars are very frequent. But currently it is still very complicated from the observational point of view to precisely measure the amount of brown dwarf and free-floating planets that form after a stellar burst. And the reason is that those are the faintest objects and the most challenging ones to detect. So as I was mentioning, now it is relatively simple to study the stellar mass content of the initial mass function. Especially now with Gaia, it is relatively simple to identify groups of stars which were formed together in the same starburst, thanks to the extremely good precisions in the astrometry of Gaia. However, if we want to study the low mass end of the IMS and the substellar content, most of these objects still escape from the Gaia detection limit, and we need ground-based images to identify those objects. This becomes especially true in star-forming regions where the stars and planets are still embedded in the parent molecular cloud and where the levels of extinction are very high. And then we need not only images in the optical where Gaia operates, but it's also very important to have images in the infrared where we can see through the extinction and through the dust. And this is exactly the idea of the Cosmic Dense project. This was an ERC project from Hervé Bouy, my PhD advisor, and this was also the idea of my PhD. So basically, we did our own observations to provide catalogs of nearby star-forming regions. Then we use statistical tools to try to identify the few hundreds of members of these star-forming regions from the vast amount of millions of background sources like faraway stars and galaxies. And finally, with this comprehensive list of members, we can eventually study the process of star formation and stellar evolution. With this slide, I want to illustrate what I was mentioning. So this importance of having these ground-based images. Here you are seeing some of these dense images that we obtained from the ground in a high extinction area and in a low extinction area. And these yellow circles correspond to the Gaia detections. So it is very noticeable in both cases that Gaia misses many of the sources that we can detect in our images, and those are crucial to identify the lightest objects, members of this region. And in this sense, there is a new survey coming. This is the Visions survey led by Stefan Mengast and Joao Alves at the University of Viena. And it is a survey with the Vista telescope at ESO that aims to catalog the star-forming regions observable from the southern hemisphere. After this brief introduction, now I would like to present you the area where I did my PhD and where I searched for these free-floating planets. So in this image, you are seeing an area of 170 degrees squared in the sky, which encompasses here the area of Upper Scorpius, which is an OB association which has between 5 and 10 million years and is part of the Scorpius-Centaurus complex. And then also here you can see the clouds in Ophiuchus, which are younger. They only have between 1 and 3 million years. Star formation is still ongoing in the region of Ophiuchus. But it has the complexity that this paramolecular cloud difficults a lot the identification of young stars in comparison with Upper Scorpius, where the paramolecular cloud has already vanished, leading to relatively low degrees of extinction. Then what we did, first of all, is try to map this whole area. And for that, we carried our own observations, and this gave me the great opportunity of visiting some of the largest telescopes on Earth. This was certainly one of the best parts of my PhD, having the opportunity to visit all these telescopes. And we combined our own images with all images public in public archives. And with this procedure, we were able to collect around 75,000 images, which were taken over the past 20 years. And this time gap is very important because, as I will mention afterwards, we will try to compute proper motions, and the larger is the time span, the more precise the proper motions will be. Then it's also maybe worth mentioning that these images come from 18 different instruments. This certainly introduces a lot of complexity in the data reduction and analysis, but this is the only way of having the large data set that we had, and which finally allowed us to detect the faintest objects in our images. And also another number I found impressive for reference is the number of individual source detection in the images, which you can see is similar to the final size of the Gaia catalog. And also, so this was possible, as I mentioned, by making use of all the observatories available on Earth, and thanks to the large collaboration with scientists from many different institutes. Then, with these images that we reduced and analyzed, we built what we call the dance catalog, which contains finally positions, proper motions, and multiband photometry, both in the optical and the infrared. And our final catalog contains 26 million sources. We combine this dense catalog with the Gaia catalog in the same region. And the Gaia has the advantage that has a more precise astrometric solution. Also, it has the great advantage of having the parallaxes on top of the proper motions, but it only has optical photometry and doesn't have photometry in the infrared. Finally, we also considered the Hipparcos catalog, but this was just to have the most complete census possible and to include the giant stars in this star-forming region. And for instance, the giant star Antares, it's too bright to be observed with Gaia, it saturates. So to have a final complete catalog, we also included Hipparcos. But it's important to say that the bulk of the analysis was done with Gaia and DENS. And then here you are also seeing a diagram where it shows the precision in proper motions as a function of the magnitude. And what is clear here is that for bright stars, Gaia has the best precision possible. And we use Gaia proper motions whenever they are available. Here, the advantage of DANCE is that it still can provide us proper motions 6 magnitudes deeper than Gaia with relatively good precisions. And all these sources will be fundamental to finally identify the substellar objects in these regions. So this is where the power of this ground-based effort is. And now what you are seeing is one of these images that we reduced as part of the DANCE project, and where you can see, well, this is one of many images in the region of Upper Scorpius. You see many stars and galaxies. And now I have a question for you, and maybe one of you can dare to say what you see at the center of this image. Don't know if you have any ideas or, well, otherwise, what you should be seeing is this tiny little red dot at the center of the image. This is one of the free-floating planets that we managed to identify. And to me, so it is impressive, not only that we have the capabilities to detect this tiny little red dot, but also we are able to measure its proper motions with a precision sufficient enough to classify this object as co-moving with the rest of stars in this complex. Now I will try to briefly explain the membership analysis. So how did we manage to detect and classify this object as part of Upper Scorpius? And basically our membership algorithm is an expectation maximization tool which classifies independently the field and the cluster population. And this algorithm was developed by Luis Massarro and Javier Olivares. And basically it models the field population with a Gaussian mixture model, both in astrometry and photometry. And the cluster population is modeled with a Gaussian mixture model in astrometry, as you can see here, plus a principal curve in different color magnitude diagrams. Then you need an initial list of members of the cluster you want to to study, but this initial list can be slightly contaminated and it can be incomplete. It is just to find the locus of the cluster in the parameter space that we want to use. Then this model works iteratively. First, you compute the cluster model. You compute membership probabilities for all the sources in your catalog, and you classify them between cluster and field members. And finally, once you have the new cluster list, you can update the cluster model and continue this process until the algorithm converges. This approach has the great advantage that it allows us to combine into the same analysis all the information that we have. That's to say, we can put into the same box all the astrometry and photometry information. We can also account for the uncertainties in these observables. And finally, we can also take into account sources which have complete information. That's to say, sources which may have optical photometry, but not photometry in the infrared or the other way around. Then what we did is apply this membership algorithm to the catalogs I have just presented. And finally, we found 3,500 members of this big region, which is Upper Scorpius and Ophiuchus here. And from all these members, between 70 and 170 have planetary masses. Those are the ones we call free-floating planets, and are those identified by red circles in this image. And you can see that they occupy both the region of Upper Scorpius and Ophiuchus. Then we took this new membership analysis of this region and obtained the magnitude distribution. This magnitude distribution has the great advantage that is a direct product of observables, and thanks to the large number of statistics, so the large number of members that we found in this association, this magnitude distribution, you can see it has a great level of precision, and then we can study all kinds of features in this magnitude distribution. I find especially interesting this dip at planetary masses. This dip is one of the first times that it has just been discovered very recently. And I think the fact that we observe it in Upper Scorpius, which is a very young region of less than 10 million years, it probably indicates that this dip should somehow be related to the formation or early evolution of these objects. And also, we can start to pose new questions, for instance, whether this dip is related to different formation mechanisms, or whether this is indeed the real frontier between brown dwarf and planets. So currently the definition of the boundary between brown dwarf and planets, it's in terms of masses, and any object beyond 13 Jupiter masses is considered as a planet, and anything above is a brown dwarf. But maybe this dip would indicate that in terms of formation, the boundary would be at a different position. Then for comparison, here we are seeing the magnitude distribution that Gaia observed in the nearby solar neighborhood in a bubble of 100 parsecs. And you can see that also in this sample, there is a dip at these planetary masses similar to the one we observed. The difference is here we are observing stars of all kinds of ages, because this is considering all the objects in 100 parsec bubble, whilst the previous slide I was only showing young stars. Then we can also compare the magnitude distribution in Upper Scorpius with previous studies, which already showed that free-floating planets are very numerous. So here we are seeing a previous study in the same region of Upper Scorpius, also in Sigma Ori, and in this open cluster NGC 1333. In all cases, we see that free-floating planets were numerous, but I think the great advantage of our new study is that it provides a way larger sample. You can see that we gain an order magnitude in the number of members in this region, which helps us to better constrain the precision on this magnitude distribution and allows us to statistically obtain more robust conclusions on this region. Then we want to convert this magnitude distribution into a mass function. But this transformation is not it's not obvious and it's not trivial, because we need to rely on evolutionary models. Here you are seeing a color magnitude diagram where I have overplotted the models at 3 and 10 million years. And you can see that only with a 7 million year time difference, an object of 0.01 solar masses would go from this position here down here. So it moves quite significantly only with this 7 million year time difference. And this means that if we don't know the age precisely of this region, we automatically will have an uncertainty on the masses inherited for this reason. So taking this limitation in mind, we still computed individual masses for all the stars, and we measured the mass function. So here, the top panel shows again the same magnitude distribution we already commented. And in the lower panel, I am showing you the mass function of this region, taking into account so here the lower and upper envelope correspond to the lower and upper limit in the ages. In this case, taking into account an age between 3 and 10 million years. Still, with this age uncertainty, which is inherited in the mass function, this is a relatively precise mass function compared to previous results. And also, it's worth saying that at high masses, the slope of this mass function is compatible with Salpeter slope, similarly to what has been observed in many other regions. And it is also important to mention that at low mass, we observe a high fraction of free-floating planets, and we estimated a very low contamination rate using synthetic data. So we estimated a low contamination, which has now been proved with spectroscopic observations, as I will comment in a few slides. But this small contamination means that this high fraction is true, and it is in fact just a lower limit because we are likely missing the most extinct objects in this region. So now we want to use this mass function to compare it with numerical simulations and try to understand if we can constrain somehow the origin of all these free-floating planets. So here in red, I show again the same mass function, and the two black lines indicate the results of numerical simulations. In one case, the stars and planets are mainly formed by only core collapse, and the second one has a slightly better resolution, and we can resolve these fragmentations into some circumstellar disk. But in both cases, it is noticeable that we have a large fraction, we observe a large fraction of free-floating planets with comparison to these models. And then the question is, what is the origin of all these free-floating planets? To try to answer this question, first we compare the fraction that we observe with the predictions of these simulations, and we found that at least, probably at least 13% of the free-floating planets we observed were formed by core collapse. That's to say, similar to low mass stars. But here it is clear and evident that there is a large fraction of free-floating planets which is not predicted by these simulations. And then we studied the possibility that some of these free-floating planets were formed in planetary systems, like exoplanets, and eventually were ejected from their parent systems due to dynamical instabilities. In short, what we assume is that the fraction of free-floating planets that were ejected by this mechanism has to be proportional to the number of stars which host giant planets times the number of planetary systems that become unstable times the number of planets per system that are eventually ejected and escape their planetary system. By plugging in some numbers which come from exoplanetary surveys and from our knowledge of planetary systems, in this case, we could estimate that this formation mechanism is also important, and at least 10% of the free-floating planets that we observed formed in planetary systems and afterwards left their planetary system. I would like to stop one moment here because I think in this case, the take-home message of our study is not so much the percentage of free-floating planets that formed by each mechanism. This certainly needs of more studies in order to better constrain these numbers. But I think the really important result is that only one of the two mechanisms alone can probably not explain the large population of free-floating planets that we found. And in fact, it has to be a combination of at least these two mechanisms and maybe even others to explain this large fraction. And also the other question that needs to be solved is whether this fraction of free-floating planets that we are observing in Upper Scorpius is universal, or maybe in other environments we will find different fractions. And for this, it is of paramount importance to do and carry similar studies of large regions in the sky where we have large number statistics to see whether this fraction is universal or not. So now, very briefly, I would like to mention that we took some of these faintest objects in our sample and we selected them for spectroscopic follow-up. We obtained spectra, low resolution spectra with EMIR at the GTC and with SWIMS at Subaru. And in fact, the majority of targets that we observe have been confirmed to be young free-floating planets. Only one of them is not yet clear that it is a young dwarf, but this spectroscopic campaign led to a confirmation rate very high and confirms that only around 6% of our samples is contaminated. And this is a contamination rate way below the majority of previous surveys of substellar objects. And we believe that it is because we combine at the same time information on proper motions and photometry. And so the proper motions add a lot of valuable information and help us to reduce a lot the contamination rate. So before finishing the talk, I would like to spend a few minutes commenting also on stellar ages. I hope I have motivated the importance of having precise stellar ages in order to have precise masses and in order to also constrain better the mass function. There are many methods to determine stellar ages. But the difficulty is that different methods can lead up to discrepancies of the order of 50%. And also different methods are best applicable at different ages. And eventually it is not straightforward how to precisely determine the age of a stellar group. In particular, many methods rely on evolutionary models, but those are especially uncertain at very young ages and for very low mass stars. And in this sense, so during my master's in Barcelona, I started to work on a method which doesn't rely on evolutionary models, but only takes into account the kinematics of an association to determine its age. Basically, this methodology needs to know precisely the positions and velocities at the present time. And then, assuming a galactic potential, one can trace back in time individual orbits of each star, and then see when a group of stars was most concentrated in the past. And at some point, one can define the time where the size of this association was smallest as the age of the association. This method was used before Gaia, but the uncertainties were very high because the samples were quite contaminated, and also the precisions in the astrometry and spectroscopy were not enough for this method to be successful. However, I think this picture is starting to change now thanks to Gaia, because we have samples which are much more precise. The contamination rates of our sample have significantly reduced, and now we can trace back in time the orbits with a much better precision. However, Gaia alone is not yet enough, and now what we need is strong efforts on obtaining spectroscopic radial velocities which have similar precisions to the Gaia astrometry. During my PhD, I also had some time to test this method on the Beta Pictoris moving group. For those who are not familiar with Beta Pictoris, this is a young stellar association of around 200 members at only 40 parsecs from the Sun. So it is very close, and it is very loose also. It is not like an open cluster. And several disks and planets have been detected around members of Beta Pictoris, and this is why it's also very important to precisely know the age of this young local association. Then we applied this traceback methodology to this association, and we could determine a dynamical traceback age of 18.5 million years, which is for the first time compatible with isochronal ages. And again, so I think the success of this method was that now, thanks to Gaia, we could reduce a lot of the contamination of the group, and also we did a strong spectroscopic campaign to select very precise radial velocities to complement Gaia. And finally, so now I'm working on a similar study in Upper Scorpius, and I'm trying to determine dynamical ages in this area to try to finally obtain more precise mass functions. But in this case, it's a bit more complicated because the region of Upper Scorpius and Ophiuchus has a rich substructure, which we have first to analyze, and we have first to detect several groups in this 3D positions and 3D velocities space, because our preliminary results already show that each of these groups are likely to have different ages. And this will be very important, as I was saying, to understand the star formation history of this region and eventually obtain a more precise mass function. So this is all I wanted to present today. I leave you with this final slide summarizing what I have been discussing today. So I presented the first large homogeneous sample of free-floating planets, which helped us to try to understand from the observational point of view which is their origin. And we proposed that at least core collapse and ejection from planetary systems have to be considered to explain the large fraction of free-floating planets that we found in this area. I also showed that a spectroscopic campaign confirmed that the contamination rate is very small in our sample. And finally, I'm also working in a methodology to determine precise stellar ages, which will hopefully try to help to better constrain the mass function and understand the formation of these objects. Thank you very much for your attention, and I'm happy to take questions if you have.
Okay, thank you, Núria, for this very nice talk. So now the session is open for questions. So please raise your hands on Zoom so that we can give you floor for your questions. Okay, come on, don't be shy. Okay, Rainer has one. So yeah.
Yes, I'll
Okay.
approach here. So my question was, so to clarify again, so you need core collapse and ejection. You said you need a minimum of 10% for both of those. And that basically includes also embryo ejection, all these other things, right? Because you had like 4 different mechanisms for explaining the free floating planets. So basically there's 4 mechanisms. Yeah, you mentioned 2, but I think like ejection and embryo ejection is more or less the same thing, right? When you say this.
So yes, in fact, this is so the way. Maybe I will go to the slide. Yeah, here. So yes, so here the way I constrain this value is by comparing with numerical simulations, and here it depends on the physics they put in these numerical simulations. In this case, the ones which I used to compare, in one they only have the resolution enough to see core collapse, and in the second one they also see this fragmentation. To my knowledge, and I have to say I'm not an expert on these simulations, but to my knowledge, they didn't directly include embryo ejection. This is something I would need from the numerical simulation point of view to have in order to compare, but sure.
So how these simulations, how much can we trust them? I mean, this is not, this is not like a critical, my question is, I know it's the only way of kind of assessing it, but do you think they're mature enough? I mean, for me, it's not surprising, the finding. I think it makes a lot of sense, but still, I mean, these simulations, we all know they're always limited.
Yes, sure. And also I come from the observational point of view, so I would have a tendency to trust more maybe observations to simulations just because I know them best. But I think in this, at the stage where we are now, so there's a lot of work to do from all of the sides, I would say. From numerical simulations, I would ideally like to have simulations where they include not only, as I was mentioning, core collapse, but other formations like you were mentioning embryo ejection. But ideally, it would be excellent if they can manage to also include planetary, if they have the resolution enough to have protoplanetary disk formation, so they can not only resolve these fragmentations, but also core collapse. This would help to put all the mechanisms in one single simulation and then compare the final results to our observations.
Do you think is there any chance to test? I hope my question, is there any chance to test, for example, ejection observationally to trace back a planet to its origin system?
And this is also a great question. Here, the problem is that, so now for these free floating planets that we obtained, we have their positions and proper motions, but we are still missing the parallaxes and the radial velocity. So I don't think we have, they are too faint to have these pieces of information, and eventually I think those are quite important for this kind of analysis. So you could maybe try to do this in 2D, but I think that the level of uncertainties that you would have is very big, and I'm not sure how confident you could be on the results.
Okay, there is another question by Isabel.
Hi. Congratulations, Núria. Nice talk. I have a question concerning what you've said of the follow-up observations with the James Webb Space Telescope and ALMA. Do you already have some program focused on or devoted to such a follow-up? And related to that, is there any project for the next Vera Rubin observatory in which you would be able to detect much fainter objects or even with ET later on?
Yeah, so it's great that you asked this, because this morning I submitted an ALMA proposal for trying to characterize, in fact, these free-floating planets. So the idea would be to try to see if we can detect disks around these free-floating planets. So far we have already detected some of them to have an infrared excess. So we believe that some of them have indeed disks, but with ALMA we would be able to first confirm the presence of the disk, and maybe by measuring ideally the mass distribution, we could compare it to the stellar content and the stellar type of disks that we find for in stars. And this comparison would also be very important to try to understand the origin of these planets. For instance, if we find similar fractions to the fraction we find for stars, this would indicate that probably these free-floating planets formed in a similar way to stars. On the contrary, if we find much smaller fractions, or we find disks which have been truncated or very small perturbed disks, maybe this would indicate that an important fraction formed by ejection from planetary systems, and in this ejection, they could somehow be truncated, or the disk could have suffered from this process. This is maybe regarding ALMA, and regarding the James Webb. So we don't have any proposal yet, but we will try to submit one for the next call that they will open. And here, I think James Webb can help us a lot to study the atmospheres of these objects. So now with the low resolution spectroscopic campaign that we have, this is in fact very low resolution. We only have the continuum, and this is just used for confirmation. So it allows us to confirm that they are young and they have planetary masses, but we don't have the resolution for knowing the composition of the atmospheres. And here it would be very interesting already to characterize the abundance of these objects, and also to compare it with planets which are part of planetary systems, because again, this could give us information on their origin. If they have similar composition to the exoplanets in planetary systems, that maybe could indicate that the origin is somehow connected.
Okay, so may I have another question?
Yeah, sure.
It is related just with the 2 slides later. So
2 slides here.
Yeah, so that one, when you trace ages dynamically. So it's just a question of ignorance. Is it enough to calculate the minimum distance between the objects to be sure that they are really bounded?
So in fact, this whole strategy is only valid under the assumption that the stars are not bound, because we treat them as test particles in a gravitational potential, but we don't take into account the interactions among stars. So this is a very important assumption of the method. And I think in the case of, for instance, beta Pictoris, this is true because these stars have a very low density. So they are already very dispersed, and so we know that they are not gravitationally bound. But this technique would not be so valid in, for instance, systems which we would know that they are gravitationally bound and where the interactions among stars would be important.
Okay, thank you, and congratulations.
Thank you.
Okay, other questions?
I think we have
Someone
here
wants to
one
make a
at the
question?
room.
Okay.
Can I do it, Francisco?
Yeah, sure, sure.
Okay. It's related with the spectra that you show on,
Yes.
on the objects.
Yeah.
Do you have any clue about what is the composition of the object that produces that kind of a spectra? I need some units here.
Yeah, hopefully we will publish this soon, and otherwise I can show you the full spectra. But this is, as you see, it's very low resolution. So here we don't have the individual lines.
No,
No.
I'm coming from the planetary system.
Okay.
Stuff. So for me, this is really specific kind of spectra, but it's really incredible that we can find an object of 10 Jupiter masses with the spectra that I should see. That's why I ask. Any clue about the composition of that?
So as far as I understand, so we cannot determine yet the composition with this. I think we would need a higher resolution spectra for that.
I'm seeing this as a planet.
Yes.
You're seeing this as a star.
Yes.
That's why.
Yeah. So I think the answer is that we don't know yet the composition just with this spectra. I think with this spectra you can somehow infer the mass, given that we also know the distance, because we are assuming it belongs to the association. Then we also can know that this is a young planet, but because here at this specific wavelength, we have this particular triangular shape. This helps us to know that this is a young dwarf. More older objects have a more flatter part. And another thing that we use to confirm their youth is by comparing with library spectra in other regions of young and more evolved field stars. So this is the type of hints that we have to know the properties. But again, the composition, I think only with this data, you cannot infer it. I think we would need higher resolution, and for this probably we need the James Webb. So I'm sorry, but I think I cannot know more.
But you see absorption bands, so it's probably water absorption or methane, no?
No. But in planets, we make this interpretation with reflected. Okay, that object can reflect some.
But the point is, so because in planet you have the nearby star, but those are isolated, so you don't have the nearby star. So you only see. No, I think you all. Yeah, exactly. So I think you don't only see the emission. Yeah, sorry, I was not understanding. So you only see the emission from the planet in principle.
Okay, any further question, either in the room or in Zoom?
I need to say something.
Yes.
Okay.
So for those of you who are still listening online Granada, so please let me know if you're interested on joining us for dinner. So we will be currently 4 or 5 persons. We take Núria out to dinner tonight, and particularly among the young ones, the students. And so please use your occasions to do some networking and get to know someone who's successful. Okay?
Thank you. Thank you very much for inviting me in Granada once more. I'm very happy to be here today. Thank you.
Yeah, thanks to you, Núria, for this very nice seminar. So a seminar on Tuesday and another colloquium on Thursday. So see you next week. I will stop recording now.